One of the purposes of college algebra is to give you exposure to some analysis. How do we analyze mathematics? And this takes you beyond what you're probably accustomed to, where mathematics is just a series of one rule after another, and you practice these skills and you learn how to solve equations and solve problems. Well, with this course, particularly starting in the later chapters, but even for the moment now, you start to get some exposure to how we analyze things using mathematics. And that really does take it to the college level. So you've been working with the quadratic equation of the form ax squared plus bx plus c equals 0. And we've solved it. There's the quadratic formula. Now what's kind of interesting to look at is what happens when this part under the square root is a certain kind of number. So we call that b squared minus 4ac. We call this the discriminant. And so what happens if it's 0? What if it equaled to 0? Then x would be simply minus b over 2a. And so, for example, if you're looking at, what would be a good example? 4x squared. I gotta think a minute to come up with this. I think it'd be a 12. 12x plus 9 equals to 0. Yeah, I think that will work. The discriminant, a, b, and c, b squared minus 4ac would be 12 squared minus 4 times 9. And 12 squared is 144, and 9 times 16 would be 144. 9 times is 16. So it equals to 0. Well, it turns out, actually, when it equals to 0, that means your polynomial was a perfect square. And by that I mean that it could be factored as a perfect square. In other words, this would be 2x plus 3 times 2x plus 3 equals to 0. Or 2x plus 3 squared equals to 0. In either case, x will be equal to a single answer. Negative 3/2. So we get a single answer in this very special case when the discriminant is 0. Okay. And not only that, if your a, b, and c are fractions or integers, we call those rational numbers, numbers that can be expressed as integers or fractions. If that was the case, then your answer would also be a rational number, a single rational number. So that's this special case. Now, what if this is negative? Okay. So if your discriminant is negative, that means that I'm taking the square root of a negative number, which means we're going to get complex numbers. So for example, if you had x squared plus x plus 1 equals to 0, then x would be minus 1 plus or minus the square root of 1 minus 4 over 2. And x would end up being minus 1 plus or minus I times the square root of 3 over 2. Alright, well, indeed we got a complex numbered answer. And in fact, it gets a little better than that. We call them complex conjugates. Because if we wrote those answers separately, let me do it up here. One answer is minus 1 plus I times the square root of 3 over 2. The other one is minus 1 minus I times the square root of 3 over 2. Then these are identical, except for this middle sign is opposite. So when two binomials are identical except for the middle sign, we call those conjugates, just the name for them. And when you multiply conjugates together, you get a difference of squares. You get interesting things happen. But anyway, we would say these are complex conjugates. By the way, all this is itemized in my book, but I wanted you to see it unfold on the board here. So, but that's always going to happen, provided your coefficients are real numbers. All right, when they're real numbers, then your answer is going to be complex conjugates if the discriminant is negative. All right, now, so we took care of the negative case, and then that leaves the positive case. Well, the positive case could really be split up into two variations. For example, if, suppose that, let's look at this equation. X squared, and I've got to think about this, minus 7x plus 12 equals to 0. All right, if we solve this by the quadratic formula, x will be, let's see, 7 plus or minus the square root of negative 7 squared minus 4 times 1 times 12 all over 2 times 1. So x equals to 7 plus or minus, and here look what we get. We get 49 minus 48, square root of 1. All that's over 2. And the square root of 1 goes away because it's a perfect square. And we'll actually get two different rational answers here. So 7 plus 1 is 8 over 2 is 4. And 7 minus 1 is 6. 6 over 2 is 3. So we have two answers. Now, so here's what I draw your attention to. When b squared minus 4ac is a perfect square, by that I mean, an integer that's squared, like 1 or 4, 9, 16, 25. When that happens, then the square root is going to disappear because it's going to simplify to an integer, provided your coefficients are integers. So we have coefficient integers, integer coefficients, and the discriminant is a perfect squared number, then the answer is going to be a rational answer. It'll be rational numbers. They won't be square root type numbers, irrational numbers. They won't be complex numbers. And what's even more interesting to me is that when this happens, that means you could have solved by factoring. And so it turns out that the only time a quadratic polynomial will ever factor when you're working with integer coefficients, the only time that happens is when the discriminant is a perfect square. And a perfect square in this case would also include 0. 0 squared is 0. So that really is a necessary criteria for factoring. And so that's why people like me can look at these and determine pretty quickly if a polynomial can be factored. And because we're thinking about the discriminant. All right, if it's not a perfect square, then you're going to get irrational answers because the square root will not completely go away. And the square root of if we're working with integers, the square root of an integer that's not a perfect square is irrational. And so in other words, you'll get, if you went to decimals, it would be a long decimal answer. So there's the case there. So discriminant positive means either two irrational answers or, in a special case, two rational answers. So anyway, I've kind of gone through all the cases there with the discriminant. And this is all cataloged, well, not only in my book, I'm sure it's cataloged in the textbook as well. So, but that's the case with this. And later we use an idea, well, actually we use something very similar in conic sections in our trigonometry course to determine if an equation represents a circle, an ellipse, a hyperbola, a parabola, or something else. And so the idea of discriminant shows up in other places in mathematics as well.